So now that we have a nice whitewater source set up, let's go ahead and set up the simulation for this. So I'll drop in a DOP.NET and I'll call this whitewater sim, then dive inside here. And we're going to need a whitewater solver, connect that to the output, and we'll need a whitewater object, connect that to the first input of that whitewater solver. And you might assume that we also need to add a gravity in here, but on the whitewater solver, this actually has gravity built into it already. So if you look at the forces tab here on that solver, there you can see some existing gravity. So we don't need a separate node for that. And for the whitewater object, I'm just going to leave everything here on its defaults. And all of the interesting stuff we have to do is on this whitewater solver. Now this whitewater solver needs our previous flip simulation as input. And if you mouse over the volume source parameter here, this gives you a hint about the data that it's expecting. It needs the liquid velocity volume and the signed distance field, and we're already bringing that in when we import the simulation up here. We've set up the sim river null after that sim data that we've imported, and this already contains that surface and velocity, so we can connect that parameter to this sim river null. So going back to our DOP.NET on that volume source, I'll open up that selector, connect that to sim river, and now the whitewater scale is essentially going to be the resolution of our sim. This is a particle separation here, so I'm going to leave this on its default for the moment, but we will likely need to turn this down for some more resolution. And similar to our flip river simulation, we also have a voxel size here, which is used for some of this solver processing. The tooltip actually gives us some extra information about it. It mentions that the volume is used for emission limiting, foam erosion, repellent seeding, and we'll talk about some of this stuff shortly. But it also gives you a hint that the voxel size should be at least twice as large as the whitewater scale. So I'm just going to link this to that whitewater scale, multiply that scale times 2. So let's copy that whitewater scale parameter, paste a relative reference into the voxel size, and then multiply that by 2. We don't need to mess with the foam location or depth range. I'm just going to leave those at their defaults, but we are going to add state attributes. So as the whitewater solver simulates these particles, those particles can lie on the surface of the water, in which case they're considered foam. They could be launched into the air, in which case they're considered spray, or they could lie inside the surface of the river, in which case they're considered bubbles. So by turning on this add state attributes option, we'll have that information available to us so that we can treat those particles differently based on that state if necessary. And moving on, I'm going to leave all of the forces parameters on their defaults here. I actually found all of this stuff to work fine as it is. Of course, you can finesse the gravity and the buoyancy of these particles, and we have some ramps available to really control these things and finesse them a bit further. I didn't find that necessary here, but feel free to have a play with that if you'd like. And then moving on to the limits tab, we need to set up the bounds for the simulation. And I'm going to set this up similarly to how we set up the river bounds. So we're going to import the actual river area geometry for this. And while we're at it, let's also set up that geometry as a collision object as well. Now we do already have some collision objects set up and cached out in this river close-up section here. So we can directly reference these nulls here from that cached out collider. But I generally like to keep setups fairly self-contained, so I don't really want the DOP.NET to reference these collide geo and volume nulls directly. So going back to the whitewater setup, I'm going to object merge in both the collision geometry and volume. So let's drop in 2 object merges for those. One for the geometry, one for the volume. And I'll connect the first one to object / river closeup / collide geo, and then drop in a null after this, and call this collide geo. And if you display that, you can see this gives us our collision geometry like expected, and we can do the same thing for the volume. So on the second object merge, I'll point this to object / river closeup / collide vol, and drop in a null for this one as well, and call this one collide vol. So there we go, we have that SDF volume as well for those collisions. And now we can set up a bounding box to set up our sim bounds, and I'll base that on the collision geo here. So drop in a bound, connect that to collide geo. You can feel free to add some padding to this if you'd like. I'm just going to leave it as it is though. And then I'll add a null after that bound SOP, and just call this bound so that we can reference this inside the DOPNet. So diving back inside our Whitewater Sim DOPNet, on this Whitewater solver, we can set the limit center to be the centroid of that bounding box. So I'll point this to .. / bound. And for that x centroid, we'll put in d_x, and then copy this, paste this into y and change that to dy, and the same thing for z. And we have to set the size as well. So for limit size, I'll use the bbox function and point that to .. / bound, and then look up d_x size. So let's copy that, paste that into y, set that to y size, paste it into z, set that to z size. And if we left click on each of these parameters, you can see this is fetching those values correctly. And if you rewind that sim, then you can see our bounding box displayed in the viewport here. So now let's add the collision object as well. So I'll just add in that static object. And for the SOP path, let's link this to collide geo. And under collisions, let's set the volume mode to volume sample and connect that to our volume VDB. So under proxy volume, I'll connect this to collide vol. Then drop in a merge, drop that just after the Whitewater solver, connect the static object to that, and then with the merge selected, I'll hit Shift R to reverse those inputs, because the default merge behavior is for the left to affect the right. So unless you set that to mutual, you have to make sure that the order of these things is correct in that merge. Now we're getting closer to running our initial sim, but we still haven't set up our emission just yet. So back on the Whitewater solver, let's go to the emission tab, and we'll point this emission source to that Whitewater source that we've set up. So open up our selector, point this to source Whitewater. And most of this stuff here we can leave at its defaults. Don't need to mess with the emission amount, or the velocity offset, or velocity multiplier, or the max initial speed, that's all fine. This lifespan, however, is going to be quite important. And this isn't a guaranteed lifespan. If you mouse over this, it says it's the average lifespan of a whitewater particle, so this can vary. And this is also affected by the parameters under the Advanced tab here. So if you expand that, you can see we have additional aging rates for the bubbles versus the foam versus the spray. So for example, we might not want the spray to age quite as fast as the bubbles or the foam, because if these particles are launched into the air, we want to allow those to travel with a bit of that ballistic trajectory before they get just deleted. So let's leave this as it is for now and see what our initial sim looks like. So let's go back to that simulation scale static camera and play through some frames. So after playing through some initial frames here, you can see we do have some initial whitewater being sourced, so this looks all good so far. But these points are quite sparse at this point, so I'm going to turn this up a bit higher and then flipbook some more frames. So let's rewind to that start frame and then make this higher resolution by turning down the whitewater scale. I'll turn down this particle separation to 0.05 and then flipbook some frames to see what this looks like. Now these initial frames of our simulation are looking quite promising. We are getting tons of whitewater being emitted, so I'm going to really crank up the aging on these and lower the lifespan so that they die out a bit more readily and we don't get so much whitewater accumulating. But overall, this is looking quite cool. So let's move on to finessing a few things here. So let's take a look at the foam tab on the Whitewater solver. So on this foam tab, I'm going to just leave the default clumping behavior here, but I'm also going to turn on erosion. And what this erosion will do is this will erode the patches of whitewater particles that are forming, and it does this based on the density as well. So let's see if we can find a decent patch of whitewater here. It looks like this patch is a decent one to look at. So as it applies the erosion here, it's eroding the edges first because those are lower density areas. And this sort of natural decay of these whitewater patches does add a lot to the simulation. This whitewater wouldn't look nearly as nice if these particles were to just disappear randomly, or if these patches of whitewater were to just live forever. So that erosion works quite well. For my simulation, I expanded the depth range of that erosion a bit, turned that up to 0.2, and increased the strength to 0.7. But of course you can finesse these things to your liking. And moving on to the repellents, this is quite interesting because this adds extra particles into the simulation that repel the whitewater particles from them. This helps to kind of create a cellular noisy look. And if you go to the Houdini whitewater documentation, there's an image here that illustrates this quite nicely. So scrolling down to the repellent section, you can see this image here where this whitewater sim is broken up by these sort of cellular holes. And these repellent particles are advected with the simulation to travel with our flip sim velocity so that this pattern kind of flows nicely with what the simulation is doing. And we have options to randomize the size of these repellents and their strength and etc. And if we play through this final shot, you don't see that cellular pattern quite as clearly as you would from perhaps the whitewater from the boat wake example that we just saw a moment ago, but these repellents are likely helping to break up our overall foam a bit and to create some of these stringier shapes. Now the repellents are enabled by default on the whitewater solver, but of course we can update this to direct it to our liking. If we want the noise shape of those repellents to evolve over time, we can increase the pulse frequency range here. I don't want to crank it up too high because I'm not looking for a super frenetic change to that shape, but I'll try something around 0.7 or so. For the strength, I wound up using a much larger range than the default. I used a range from 3 to 50. Of course, as always, you can play around with this to see what sort of maximum and minimum amount of repellent force you want to apply. And then for the feature size range, this is quite important. And to dial in the feature size range, I'm going to use a size reference box to help pick the size range that we want to see here. Very similar to how we've used a size reference box a number of other times in this course. And just to quickly get that box into the correct position, I'm going to go to the Limits tab on my whitewater solver, right-click the Limit Center parameter, copy that parameter, then jump out of that DOPNet and create this box. I'll call this size reference, and then paste those copied values into this center parameter. So if we display that, then you can see this reference box right in the middle of our sim here. And this default size of 1 looks pretty big. I don't know that I want the repellent particles to be making holes this size. That seems a bit too large for our current scale here. So let's start bringing this down. It looks like a size of approximately 0.6 to 0.7 looks reasonable for the high end of the repellent sizes. But because these sizes are in a range, we can pick a minimum size as well. So it looks like approximately 0.1 or 0.2 should be pretty good. So back on the Whitewater Solver's Foam tab, let's set the size range to go from 0.15 to 0.7. And then let's see how this looks in a new flipbook. And before we run a new flipbook, let's take another look back at the previous version. And in this version, it looks like we are getting a lot of coverage from these whitewater particles. So I'm going to make these die off a bit sooner. So let's go back to the emission tab and turn down the overall lifespan. So the default is 5. So let's turn it down to I don't know, maybe a little less than half of that. And for the aging rates, I'm going to leave the spray alone so that we're not killing off the flying particles too quickly. But for the bubbles and the foam, I'm going to crank that aging rate up quite a bit. I'll try an aging rate of 20. And this previous sim was quite fast to simulate. It only took a few minutes to do this 30 frames. And for this close-up shot, I only need to simulate 100 frames to cover the entire shot range with the pre-roll. So we can crank up our resolution quite a bit. And I'm not going to crank it up all the way just yet, but we can turn it up a bit more from what it's currently at. So I'll turn it down to about half of what it is, down to 0.03 on that particle separation, which will make this much more high resolution. And then go back to our static sim scale camera and do another flipbook of this. But for this one, I'm going to run it for the entire time range. Now this latest simulation is looking quite cool. Let's set the first frame to frame 15 so we're not displaying the pre-roll. And I'm pretty happy with how this is looking. It looks like perhaps those repellent particles are a bit strong or a bit too large, so you could potentially turn down the strength or the size, or both, on those repellent particles, but I'm going to wait until we see this in context with the actual fluid surface before we decide on that, because this could very well look nice and make sense when it's in conjunction with the actual render mesh. So one more change I want to make to the simulation setup before we move on to add some extra sources is to add a little bit of extra pop wind. So everything is looking nice so far, but a little bit of wind turbulence can help things to look that much more natural. And this might be kind of a subtle effect. I'm not looking to go super heavy-handed with this extra pop wind here. And for the swirl size, I'm once again going to refer back to the size reference box. So if we take a closer look at this size reference, this current scale isn't too far off of what I'd actually like to see for the pop wind. For the pop wind size, I would go maybe a little bit smaller than this. Let's just try turning that uniform scale down a little bit more. And I think something around 0.13 should look pretty good for that scale size. So diving back into our pop wind here, I'll set the swirl size to 0.13 and turn up the amplitude a bit. And I'll disconnect our previous mplay session so that we have our old sim to compare if we need to. Now let's rewind the sim, go back to our camera, and run a new flipbook. Now this updated simulation with that extra pop wind turbulence is looking pretty good. It's not a massive difference from the previous version. We're probably getting a bit more breakup in here, and of course you can play around with more or less amplitude on that pop wind turbulence, and of course play around with the swirl size a bit as well. And I'm going to stick with this behavior for now. But the one update that I'd like to see is a bit of whitewater emission from the sides of the river, those contact areas with the rocks. Whether that's physically accurate or not, whether that would generate foam there, it would look quite nice to have a bit of that emission where the water contacts the rocks. So next we'll take a look at adding some custom sources like those.